Welcome to Pre-Calculus. Today we will investigate writing sigma notation to represent geometric series. We'll take a look at two examples where we write series using sigma notation, and then two examples where we've used sigma notation to decide what's the first and the nth term of the series. So recall that with a series, what we're looking at is really a sequence, which is just a list of numbers that are now connected with addition. So a series is a sum. And that's what we're trying to represent when we're using sigma notation. Sigma is just simply the capital Greek letter for S, which means, in our case, sum. So to do so, what I want to do first is just decide how many terms do I have here in my series. So I'm just going to number them 1, 2, 3, 4, 5, 6. So as I write my sigma notation, so there's capital sigma, I'm going to write below that my first n value is going to be 1, and we're going to add up to the 6th value in the series. What I need to decide then is what explicit formula to use. So what I'll need is my explicit formula for geometric series, really sequences. So the explicit formula, just to recall how that, how we create that, is going to be a sub n equals the first term, which we'll call a sub 1, times the common ratio to the power of n minus 1. And again, this is the explicit formula for geometric. So what we need to do is create this formula. So I just want to input my a sub 1, my common ratio, and then we'll be good to input this over here into our sigma notation. So for the first term, I can see that real clearly. That's my 4. So in this case, a sub n is going to be 4. We need to decide what the common ratio is. So I'm going to just take the terms in the series and divide the second by the first. So 16 divided by 4 is 4. We want to see if that's common. So 64 will go for the third and the second. 64 divided by 16 is also 4. And the numbers are getting very large. 256 divided by 64 is 4. 1,024 divided by 256 is 4, and 4,096 divided by 1,024 is 4. So definitely my common ratio, my R value here is 4 to the power of n minus 1. Now, when I see an instance where I've got really the same base, 4, for both of these, I can assume that this a sub 1 has a power of 1. And then I can just add up those powers since the bases are the same. So this is equivalent to the common base 4 to the power of 1 plus n minus 1. So I'm just adding those powers. And then my 1s are going to cancel. 1 minus 1, 0. So ultimately, my explicit formula is very simply 4 to the power of n. And that's what I'm going to input into my sigma notation, and that's complete. So again, what we've done here is we've taken the series, which is these 6 values added up, and we've simplified it down by representing it as sigma notation. Well, there our common ratio was a number bigger than 1. Let's take a look at an instance where it's not bigger than 1. So here I've got the series 1/3 plus 1/9 plus 1 over 27 plus 1 over 81. Again, I want to rewrite the series using sigma notation. So again, what I need to do first is just count how many terms do I have. So 1, 2, 3, 4. So I'll set up the sigma notation from n equals 1 to 4. Now I want to decide what will my explicit formula be. So we just saw how that template works. The explicit formula for geometric sequences, which will apply to this series, is going to be a sub n is the first term times the common ratio to the power of n minus 1. So just like we did with that first example, I want to input my first term, which in this case is 1 over 3. And then I need to decide what is my common ratio. So I'll do that the same way. I'm going to look at pairs of these terms in the series and divide the second by the first. So 1 over 9 divided by 1 over 3 is going to be 1/3. Let's see if that's common. 1 over 27 divided by 1 over 9, that's also 1/3. And then lastly, 1 over 81 divided by 1 over 27, 1/3. So my common ratio is also 1/3. And when I apply the power of n minus 1, again, what I'm seeing is those bases are the same value. They're both 1/3. And so what I can do with that is combine them just by thinking that the first base of 1/3 has a power of 1. So that's going to be equivalent to 1/3 to the power of 1 plus n minus 1. And again, those ones will cancel. And we're going to get that our a sub n term, our nth term, is 1/3 to the power of n. And that, again, is what I want to input here to describe my nth term here in the sigma notation. So those examples, we just have a series and we want to write sigma notation to represent the series. Let's take a look at two examples where I have sigma notation and I want to use it to find the first term and the nth term of the series. Remember, nth term describes the final term. So really we're looking for bookends, the first and the last. So I just want to use the sigma notation to describe those first and last terms. So just based on my indices here, I'm going from k equals 1 to 7. So again, if I think, what does that mean in terms of the series? I have 7 terms in the series. And to get the first term, basically I'm going to take my explicit rule 2 to the power of k, but input that k value of 1. And that immediately is going to give me my first term of 2 to the power of 1, or 2. To find my nth term, that's really looking at my last term, in this case the 7th. That's going to be, again, using the explicit rule 2 to the power of k. I'm going to input this 7 for the k, 2 to the power of 7, which means my nth term, my last term in this geometric series, is going to be 2 to the power of 7. So that's a large number. Remember, 2 to the power of 6, that's like 4 cubed, is going to be 64. So if I multiply by the 7th factor of 2, 64 times 2 is going to give me 128. And that will give me my first and my nth term. So let's take a look at one last example where we do this same task of taking the sigma notation and deriving the first and the nth term of the series. So here I have sigma from n equals 0 to 6. So notice this is a little different. I'm not looking at 6 terms, but 7. And that's because I'm starting with index value of 0. So my first term is like my 0 term. 0, 1, 2, 3, 4, 5, and 6. So if I label my terms like that, I've got 7 of them. So to find my first term, I'm going to take the explicit rule here, 1 over 4 to the power of n, and I'm going to substitute in that index value of 0 for my n value. So it's 1 over 4 to the power of 0, which is going to be 1 over 4 to the power of 0 is just 1. So that's going to be 1. My first term is 1. Again, I can do the same to find my nth term. My nth term here is the 6th. Well, it's the 7th term, but it's got the index value of 6. So again, I'm picking up the explicit formula here, 1 over 4, and I'm going to put in the power of 6. So all we have to do here is calculate 4 to the power of 6. So that's a large value. I know 4 to the power of 3, 4 times 4 times 4 is 64. So basically I've got two 64s, because 4 to the power of 3 times 4 to the power of 3 is going to be 4 to the power of 6. So what I really want to calculate is what's 64 times 64. So we'll calculate that out. 256, 36, 3, 38. So that's going to be, add the 6, 9, 4,096. Now keep in mind that's in the denominator. So 1 over 4,096. So we see with a series like this, where my common ratio is less than 1, as it goes, the numbers get smaller and smaller and smaller instead of larger and larger and larger. We would call a series like this something that might converge. 1 over 4,096. And that completes that example. Again, we're just looking to use that sigma notation to find the first and the nth term of the series. Well, thank you for joining for this investigation of writing sigma notation and using sigma notation to describe geometric series and to find the first and the last terms. See you soon.